Every planet beyond our solar system that humanity has ever found, we found by inference. We found them by watching a star flicker, almost imperceptibly, as something unseen passed in front of it. We found them by measuring a star's own faint wobble, pulled gently back and forth by the gravity of something orbiting it in the dark. We found them through shadows, through mathematics, through light bent and dimmed in ways that could only mean one thing was hiding there, even though we never actually saw it. 6,000 exoplanets confirmed since the first one was detected in the 1990s, and the overwhelming majority of every single one of them exists, in our evidence, only as an inference, a conclusion drawn from indirect clues, never an actual photograph, never a direct image of the object itself, sitting in space, reflecting or emitting its own light, captured the way you would capture a photograph of anything else you can simply point a camera at and see. In June 2025, that changed. For the first time in the operational history of the James Webb Space Telescope, the most powerful space observatory ever built, a $10 billion instrument unfolded 1 million miles from Earth, astronomers pointed it at a young star and captured something that had never been captured by this telescope before. Not an inference, not a shadow, not a wobble in starlight, an actual direct image of a planet itself sitting in the darkness around a star. More than 100 light years from Earth, photographed in infrared light by the most sensitive instrument humanity has ever built for exactly this purpose. This is the story of how that photograph was taken, why it took so long for any telescope to manage it, and what the planet it revealed is telling astronomers about how worlds like our own actually come into existence. To understand why this moment mattered so profoundly to the astronomical community, you first need to understand exactly how difficult the basic task of photographing an exoplanet actually is, and why, even with the most advanced telescope in human history, it remained essentially impossible for the overwhelming majority of known exoplanets until very recently. Stars are extraordinarily, overwhelmingly bright. Planets, by comparison, are extraordinarily dim because, unlike stars, they generate no light of their own through nuclear fusion. Whatever light a planet emits or reflects is a tiny fraction, often millions or even billions of times fainter, than the light pouring out from the star it orbits. Trying to directly photograph a planet sitting next to its parent star is, as astronomers frequently describe it, something like trying to see a firefly hovering directly next to the beam of a lighthouse from miles away. The lighthouse doesn't just outshine the firefly, it floods the entire field of view with so much light that the firefly's faint glow is completely lost, swallowed by glare before it ever has a chance to register. This single brutal physical limitation explains why, even decades into the search for planets beyond our solar system, the vast majority of all 6,000 confirmed exoplanets have been found exclusively through indirect detection methods. The transit method, used most extensively by space telescopes like Kepler and TESS, watches for the extremely subtle periodic dimming of a star's light that occurs when a planet passes directly in front of it from our vantage point. A dip in brightness, sometimes amounting to a fraction of a single percent, but detectable with sufficiently precise instruments, repeating with the regularity of the planet's orbital period. The radial velocity method, one of the earliest techniques used to detect exoplanets, measures the tiny gravitational wobble a planet induces in its host star as the two bodies orbit their shared center of mass, detected through extremely precise measurements of shifts in the star's light spectrum. Both of these methods are remarkably effective and have driven the overwhelming majority of exoplanet discoveries to date. Neither of them produces an actual image of the planet itself. They produce evidence of the planet's existence and its physical properties, inferred from how it affects the light of its star, without ever directly capturing a single photon that actually came from the planet. Direct imaging, the technique of actually capturing a photograph showing the planet itself, separated visually from its host star, is a fundamentally different and dramatically more difficult challenge, requiring specialized technology specifically designed to solve the lighthouse and firefly problem. The primary tool for this is something called a coronagraph, a technique that traces its origins back to the 1930s, when it was originally developed to study the faint outer atmosphere of our own sun by artificially blocking out the sun's overwhelmingly bright central disk, creating something like an artificial eclipse that allows much fainter structures around the blocked-out star to become visible. Applied to exoplanet research, a coronagraph works by precisely blocking the light coming directly from a distant star, suppressing that overwhelming glare enough that any much fainter light sources nearby, potentially including an orbiting planet, have a chance of actually being detected against the darkness, rather than being completely overwhelmed by stellar light bleeding across the entire image. Using coronagraphic techniques, ground-based and space-based telescopes had, prior to 2025, managed to produce direct images of a few dozen exoplanets out of the thousands confirmed to exist. But there was a critical limitation built into every one of those prior successes. Until 2025, every single exoplanet ever directly imaged by any telescope had been what astronomers call a super-Jupiter, a planet significantly more massive than Jupiter itself, the largest planet in our own solar system. This was not a coincidence of where astronomers happened to be looking. It was a direct consequence of the physics involved. More massive planets, particularly young ones, still glowing with residual heat from their own formation, are intrinsically brighter in infrared light than smaller planets, making them the only category of exoplanet bright enough to be successfully separated from their parent star's glare using the imaging technology available before Webb's most advanced capabilities came fully online. Smaller, fainter, less massive planets, closer in scale to the kinds of worlds many astronomers are most interested in, worlds more comparable to the planets actually present in our own solar system, remained, for the purposes of direct imaging, effectively invisible, drowned out by exactly the kind of overwhelming stellar glare a coronagraph is designed to suppress, but which had never been suppressed quite effectively enough to reveal anything smaller than a super-Jupiter. This was the specific technical barrier that a team of astronomers led by Anne-Marie Lagrange of the Paris Observatory and the French National Research Agency CNRS set out to address using the James Webb Space Telescope's exceptionally sensitive infrared instrumentation. Rather than searching broadly across many star systems hoping to get lucky, the team adopted a deliberately targeted strategy. They focused specifically on young stars, stars recently formed, still surrounded by the kind of dusty debris disk material that, over millions of years, gradually coalesces into planets through the same fundamental process that built every planet in our own solar system roughly 4.5 billion years ago. Young planets, the team reasoned, would still be glowing with substantial residual heat left over from their own formation, making them intrinsically brighter in infrared wavelengths than older, more thoroughly cooled planets would be, giving Webb's instruments the best possible chance of actually detecting something faint enough that older telescopes simply couldn't. The team also specifically selected systems that could be observed pole-on, meaning Earth's vantage point looks essentially straight down onto the system from above, rather than viewing the orbital plane edge-on, giving researchers an unobstructed bird's-eye view directly into the debris disk surrounding the star, rather than a view where the disk's structure would be compressed and harder to interpret from a more oblique angle. And critically, they looked specifically for visible gaps within these debris disks, distinct identifiable lanes or rings where the dust and debris that would otherwise be expected to exist appeared to be missing or significantly thinned out. Such gaps can, in principle, be created by several different physical mechanisms, including magnetic field effects or pressure variations within the disk material itself. But one of the most likely explanations for a clean, well-defined gap in an otherwise continuous debris disk is the gravitational influence of a planet actively orbiting within that gap, and, through its own gravity, clearing the surrounding material away from its orbital path. Precisely the kind of process scientists believe shaped the architecture of our own solar system's earliest asteroid and debris distributions billions of years ago. The target that ultimately produced the breakthrough was a star called TWA-7, also designated CE Antliae, located approximately 111 light-years from Earth and estimated to be only about 6.4 million years old. Astonishingly young by astronomical standards, essentially still in its developmental infancy compared to the 4.6 billion year age of our own sun. TWA-7 was already known from earlier observations using ground-based instruments including the European Southern Observatory's Very Large Telescope to possess a debris disk structured into 3 distinct separate rings. When Webb's team turned the telescope's exceptionally sensitive mid-infrared instrument known as MIRI toward the system in June 2024, they detected something genuinely promising. A faint but distinct source of infrared light, sitting precisely within a gap located between the first and second rings of the disk. Exactly the kind of location the theoretical models predicted an orbiting planet would carve out for itself through its own gravitational influence on the surrounding debris. The discovery alone was not on its own sufficient proof. Faint infrared sources detected in deep space images can, in some cases, turn out to be something else entirely. A distant background galaxy, for instance, happening to sit at almost exactly the right position in the sky to appear, from Webb's vantage point, as though it were located within the gap in TWA-7's debris disk, despite actually being located at a vastly greater distance, completely unrelated to the star system being studied. Ruling out this kind of false positive possibility required careful additional analysis. Lagrange's team calculated the statistical probability that the detected infrared source was, in fact, an unrelated background object rather than a genuine planet within the TWA-7 system, and determined that probability to be approximately 0.34%, a vanishingly small likelihood, strongly supporting the conclusion that what they we're looking at was genuinely associated with the star system itself, rather than an unrelated, coincidentally positioned object many times farther away. To further strengthen the case, the research team ran detailed computer simulations, modeling exactly how a planet, if one existed at the specific location and with the estimated mass suggested by the infrared detection, would be expected to gravitationally shape the surrounding debris disk over time. These simulations confirmed something remarkable. A planet positioned and sized according to the team's observational data would be expected to produce precisely the kind of narrow, well-defined ring structure and the specific empty gap pattern that ground-based telescopes had already independently observed in TWA7's debris disk years earlier, before Webb's direct detection of the infrared source itself. The theoretical prediction and the direct observational evidence lined up. The disk's structure, observed independently, matched exactly what a planet of this specific size, in this specific location, would be expected to create. The planet, designated TWA7b, turned out to possess genuinely remarkable physical characteristics. Characteristics that, in their own right, represented a significant scientific milestone independent of the historic nature of the direct imaging achievement itself. Estimates place its mass at somewhere in the range of 100 Earth masses, or roughly a third the mass of Jupiter, making it comparable in scale to Saturn, the second largest planet in our own solar system. Critically, this made TWA7b dramatically less, massive than any exoplanet that had ever previously been successfully directly imaged by any telescope, ground-based or space-based. Researchers calculated it to be approximately 10 times lighter than the previous lightest planet ever captured through direct imaging techniques. This was not simply Webb adding one more entry to the existing catalog of directly imaged superjupiters. This was Webb demonstrating, for the first time, that direct imaging technology had finally advanced far enough to detect planets dramatically smaller and fainter than anything achievable before, opening, at least in principle, a pathway toward eventually directly imaging planets closer in scale to Earth itself, the ultimate long-term goal driving much of exoplanet research generally. The planet orbits its host star at a distance roughly 52 times greater than the distance separating Earth from our own Sun, so I dare placing TWA7b in terms of orbital distance, somewhere well beyond the orbit of Pluto if it were transplanted into our own solar system, situated in the cold, distant outer reaches of its planetary system, embedded directly within the gap of debris disk material that its own gravity appears to be actively shaping and maintaining. The team's findings were published in the prestigious peer-reviewed journal Nature on June 25, 2025, immediately drawing significant attention across the international astronomical community. The European Space Agency, one of the three space agencies, alongside NASA and the Canadian Space Agency that jointly operate the James Webb Space Telescope, formally announced the result as representing the telescope's first direct image discovery of a planet beyond our solar system, and explicitly noted that, if fully confirmed through additional follow-up observations, it would stand as the lightest exoplanet ever captured through direct imaging by any telescope in the history of the field. What makes this discovery scientifically significant extends well beyond the historic nature of the achievement itself, important as that milestone is in its own right. TWA7b offers astronomers something genuinely valuable and previously almost entirely unavailable to them, a young, still-forming planetary system, caught in the act of actively shaping itself, observed directly rather than inferred indirectly. The debris disk surrounding TWA7, with its three distinct rings and the gap where TWA7b orbits, provides researchers with detailed, direct observational confirmation of theoretical models describing exactly how planets gravitationally interact with and progressively clear out the material surrounding them during the earliest stages of planetary formation, the same fundamental process believed to have shaped the early structure of our own solar system, including the formation of the asteroid belt and the broader distribution of rocky and gas giant planets across our Sun's own surrounding debris disk more than 4.5 billion years ago. Observing this process directly in a system still actively undergoing it today gives astronomers a genuine real-time laboratory for testing and refining theories about planetary formation that had previously been built almost entirely from indirect evidence and computer modeling alone. The achievement also carries significant implications for the future trajectory of exoplanet research more broadly. James Webb is, by design, not the final word in humanity's ability to directly image distant worlds. It represents a critical stepping stone toward even more advanced instruments currently in active development. The extremely large telescope, a massive ground-based observatory currently under construction, is expected to become operational around 2030, bringing dramatically increased resolving power to bear on exactly this kind of direct imaging challenge. Further beyond that, NASA's proposed Habitable Worlds Observatory, currently targeted for sometime around 2040, is being specifically designed with the long-term goal of directly imaging Earth-sized rocky planets within the habitable zones of nearby sun-like stars. The ultimate objective that discoveries like TWA7b represent a genuine, demonstrated, scientifically validated step toward achieving. What James Webb captured in June 2024, confirmed and published in June 2025, was not simply one more data point added to an already substantial catalog of known exoplanets. It was proof of capability, direct, photographic, undeniable evidence that the technology now exists to actually see, rather than merely infer, planets dramatically smaller and fainter than anything direct imaging had ever successfully captured before. For nearly 30 years, since the first confirmed exoplanet detection in the 1990s, humanity has understood the existence of thousands of worlds beyond our own solar system almost entirely through shadows, wobbles, and mathematical inference. Real, scientifically rigorous evidence, but indirect evidence nonetheless. Evidence describing planets that no human instrument had ever actually managed to see with anything resembling a direct photograph. TWA7b changed that. Somewhere around 111 light-years from where you are right now, a young planet roughly the mass of Saturn is actively orbiting within a gap it has carved out of its own stars. Surrounding debris disk, glowing faintly in infrared light left over from its own recent formation, and for the first time in the operational history of the most powerful telescope humanity has ever built, that faint glow has been captured directly. Not inferred, not calculated, but actually photographed. Light from another world reaching across more than 100 light-years of empty space to land. Finally, on an instrument capable of recognizing it for exactly what it was.